Hey everyone, welcome back. This is our last video on the AP Statistics practice exam for the semester A, the fall semester. And we're going to start with question 48, which is about a college basketball player. She makes 80% of her free throws. And then at the end of the game, her team is losing by 2 points. She is fouled attempting a 3-point shot and is awarded 3 free throws. Now, assuming her free throw attempts are independent, what's the probability that she will make at least 2 of her free throws? And this question really makes me think about the problem that we did in class. It's pretty much the same thing, only this player is a little bit better at free throws. Let's take a look. Is this, well, there are only 3 free throws. Let me highlight that. And the fact that she's going to do this experiment 3 times makes me think that this is a binary distribution. So let's check and see if this is actually a binomial setting. So this is a binomial setting. The first thing is B. The first thing to check is B. Is this a binary setting? And we have either she makes a shot or she misses the shot. So yes, this is binary. Next we have independence, and we are told assuming the free throws are independent. So that qualifies my I. The next one is N. Same number of, or set number of trials. And of course for this one, we're saying she's going to shoot 3 free throws. Last one is the same probability of success. And we're saying that the probability of success is 0.80, which would mean the probability of a failure, 1 minus P, that's going to be 0.20. So this qualifies as a binomial setting. All we need to know is the probability that she makes at least 2 of the free throws. If we were writing this up, we would say that X is equal to the number of made free throws, which is a binomial setting with the number of trials is 3, and the probability of success is 0.8. We want to know the probability that X is greater than equal to 2, and we can do this in a couple of different ways. First way that we can think about this, that's simply the probability that X equals 2 plus the probability that X equals 3. And that would be everything greater than equal to 2. This might be the easiest way to do it, I think. We'll grab our calculator and head to the binomial PDF setting. And then we have 3 trials. The probability of success is 0.80. And we want to know 2, the probability that she makes 2. And then we're going to add to that the probability that our basketball player makes 3 free throws. So when we add those together, we get 0.896. Now there is another way of doing this which we should talk about. And this would be to rephrase this probability from the probability that X is greater than equal to 2 into 1 minus the probability that X is greater than equal to 1. Notice that those are 2 sets that do not overlap. Greater than equal to 1, or sorry, greater than equal to 2 and less than equal to 1. That encompasses all of the outcomes with no overlap. So this would be the correct way to write that. And for this one, we would go to our calculator again, and we would type 1 minus, and this time when we go to the distribution, we're going to go to where is that, letter B, the binomial CDF. So the number of trials is 3, the probability of success is still 0.8, but now we're going to do 1 or less. When I look at the computer screen, I see that this is 1 minus binomial CDF. X is less than equal to 1 over here on the right side. And that should give me the exact same number. Of course it does. So I don't know which of those you prefer to do. Usually for these they will be kind of simple. So it doesn't particularly matter which one you use. Yeah, that's our question number 48. Let's look at 49. We've got an Alaskan transportation company claims to keep its box office receipts boxcars warmed to at least 20 degrees Celsius to keep products from freezing during transportation. The dot plot shows the results of taking an SRS of 30 SRSs of 10 temperature readings from a normal population, mu equals 20 and sigma equals 4, and showing and recording the sample minimum each time. And wow, that was a lot to unpack. So let's see what we have. We have the dot plot below, so this dot plot down here. This is 30 SRSs of 10 temperature readings. So there are 30 dots here, and each dot represents 10 temperature readings. Each dot is also recording the sample minimum each time. So these are the sample minimums from 30 samples of 10. Okay. Now, for that population, the population that it was drawing from had a mean temperature of 20 and a standard deviation of 4. So if we have a sample and we have a minimum temperature in that sample that is, low in comparison to the rest of the dots here from the population, that means that it was unlikely that the average temperature for that sample was actually 20. So that's first part here. All of this is the setup to the question. The question itself is this piece right here. So the sample minimum of a temperature of 10 trucks was found to be 6 degrees. Okay, so we took another sample of 10 and we found that the minimum was 6. And, there's only one dot here at 6. So if the population was actually 20 mean and a standard deviation of 4, that means it's very unlikely to get a minimum temperature of 6. So if it's unlikely to get a minimum temperature of 6, that's 1 out of 30 times it happened. That's definitely less than 5%. So since we got a minimum temperature of 6 in this one sample, that means that it's very unlikely that the actual mean temperature would have been 20. So yes, we can reject the claim made by the company. It's very surprising to get a sample minimum of 6 degrees or less in a sample of 10 if the true minimum was actually 20. So basically that 6 is statistically significant because the probability of 6 or less is lower than 5%. Okay, with this will definitely become much more clear later on in the semester as we continue. So let's take a look at 50 here. We've got box plots of values taken by 3 different statistics estimating a sample parameter in 30 samples of the same population. The true value of the population is marked with an arrow. Okay, so which of these has the largest amount of bias? So the largest amount of bias. So let's remember that bias means that the sampling distribution is not centered at the population parameter. So if I take a look at statistic A, if this is the population mean, yeah, statistic A is centered at the population mean for the most part. It has a high degree of variability, but variability is not the same thing as bias. Now for population B, here's the marking. This is where the population parameter is, and yes, this statistic B is centered at the population parameter. It has less variability than statistic A, but both of them are still centered at the population parameter. So no, statistic B is not biased. Statistic C, however, you can see that statistic C is not centered at the population parameter value. The mean for statistic C would be somewhere over here, maybe a little bit further over here. So that would be the mean for statistic C. It's not the same as the mean for the population. So statistic C has the same amount of bias, has the most amount of bias. Remember, in statistics, bias means that the sampling distribution is not centered at the population parameter value. 51. Suppose we wish to estimate the percentage of students who smoke cigarettes at each of several colleges and universities. Two of the colleges are Wabash and Purdue. That has an enrollment. Wabash has an enrollment 900. Purdue has an enrollment of 36,000. What should the relative size of samples from each school? What should be the relative size of our samples from each school if we want the two sampling distributions to have approximately the same standard deviation? So if I take a look at the standard deviations of some typical standard deviation, some typical sampling distributions, we get that sigma of x bar is equal to sigma over the square root of n. So we're dividing by a square root of n, so it's inversely proportional to the square root of the sample size. Over here, if I dissect the standard deviation for a sampling distribution of p hat, we get that we have a square root of n in the denominator here also. So the standard deviation is inversely proportional to the sample size. So since the thing that matters is the sample size, the population size does not really matter for the standard deviation. The standard deviation will not get larger or smaller depending on the population size, which basically means over here that when we see enrollment is 900 and enrollment is 36,000, it really doesn't matter. The only thing that matters for the standard deviation is the sample size. So if we want two sampling distributions to have approximately the same standard deviation, we should take samples of about the same size from each school. The sample size matters much, much more than the population size. At least as far as the standard deviation goes, the sample size is much more important. So let's take a look at question 52 now. I can feel the end of this video and the end of the practice final coming. We have a random sample of 1,000 Americans found that 62% were satisfied with the service provided by the dealer for their car, and a random sample of 1,000 Canadians found that 59% were satisfied with the service provided by their dealer. So now we're asking about the sampling variability. So keeping in mind what we were just talking about, the sample size of these two is going to play a big part in the sampling variability, or that standard deviation, which is a measure of variability. So both samples have have exactly the same size, and both samples also have the same similar proportions, which is to say that both populations have similar proportions. 62% versus 59%, that's very close. So without doing any calculation, I can probably tell you that these two variabilities are going to be not exactly the same, but very close. The sample sizes are exactly the same, and the population parameter, 62% and 59%, are very close as well. So let's see the other the other choices here. We have exactly the same, so maybe we should do a little bit of calculating. We have much smaller for the, actually, let's go back to A. Let's actually calculate these standard deviations since this one is saying exactly the same for letter A. So as I'm writing out these two standard deviations, we have the standard deviation for the sample of proportion for Americans, that's at 0.62 multiplied by 0.38 on the numerator. And that same thing for Canadians, we get 0.59 multiplied by 0.41. So we can see that they're actually not exactly the same. They're really close, but not exactly the same. So we can cross that out. Letter C, much smaller for the sample of Canadians because the population in Canada is much smaller than the population in the United States. Well, that's a red flag because the population of Canada doesn't matter for the sampling distribution, the sampling distribution's variability. So that one's incorrect. Letter D, the smaller for Canadians because the percent satisfied was much smaller than that for Americans. Well, okay, so we've come to it. We actually have to compute these now. Let's compute. And wouldn't you know it, actually, with these numbers, the Canadians have a larger measure of variability than the Americans. So that's actually not correct. Mathematically, when we think about it, when I think about this mathematically, since 0.62 is further away from 0.5 than 0.59, 0.59 and 0.41 actually should be a little bit larger if we're multiplying them together. Okay, last one, larger for Canadians. Well, let's see, because Canadian citizens are more widely dispersed, again, that shouldn't matter. Hence, they have more variable views. Okay, well, no, that shouldn't matter. The only thing that matters is the percent satisfied and the sample sizes. So this geometric, or this geographic distribution of the citizens doesn't actually matter. Or at least it doesn't matter with the cold, hard mathematics of the situation. So there's our 52. Question number 53. Suppose at Elkhorn High School, the number of hours per week that seniors spend on homework is approximately normal, with a mean of 18.6 and a standard deviation of 6. We have Mrs. Habrick taking a random sample of 36 seniors and calculating the sample mean homework hours per week. What's the standard deviation for this sampling distribution of means for 36 students? So Mrs. Habrick is looking at a sampling distribution with sample size 36. The sampling distributions have a standard deviation of the population standard deviation divided by square root n, which is going to be 6 divided by the square root of 36, which is just 1. So that's pretty painless as long as we have our conception that we're looking at a sampling distribution and we know our standard deviation formula for a population mean. 54 here says, suppose you are sampling from a distribution that's strongly skewed to the left. Which of the following statements about the sampling distribution for a mean is true? Okay, so let's think about the actual answer that we're talking about here, or the actual concept that we're talking about here is that central limit theorem. So the larger our sample is going to be, the more normal our population the more normal our sampling distribution will look like, even if the sampling distribution, or if the population distribution is skewed to the left. So let me try and rephrase that one more time. The sampling distribution is approximately normal regardless of the population shape. The sampling distribution is approximately normal regardless of the population shape if the sample sizes are large. So letter A, as the sample size increases, the shape of the sampling distribution gets closer and closer to a normal distribution. Now 54 That question A sounds really good. That part, or answer A sounds really good. B, as the sample size increases, the shape of the sampling distribution gets closer and closer to the shape of the population. No, that's actually not correct. It gets closer and closer to a normal distribution. C, as the sample size increases, the mean of the sampling distribution gets closer and closer to the population mean. That has actually nothing to do with the sample size. The sampling distribution will be centered at the mean regardless of the sample size because the mean is an unbiased estimator. D, regardless of sample size, the shape of the sampling distribution will be similar to the shape of the population distribution. And I think with the exercises we saw in class, that's not true. The shape of the sampling distribution changes depending on the size of the sample. The sampling distribution becomes more and more like the normal distribution. Regardless of the sample size, the standard deviation is approximately equal to the standard deviation of the population. Again, the standard deviation is always going to decrease with larger and larger samples. So all of those other questions, or all those other answers, are definitely not correct. So we can be pretty confident marking letter A here. And last question of our practice final, number 55. An automobile insurer has found that repair claims have a mean of 920 and a standard deviation of 870. Suppose the next 100 claims can be regarded as a random sample of the long-run claims process. What is the probability that the mean of the next 100 claims is larger than 1,000? So we're talking about the mean of 100 claims. We're not talking about an individual claim. So we need to be looking at the we should be looking at the sampling distribution for a mean. So 100 claims means that we're going to standardize 100. So averages are going to follow a normal distribution with a mean that's equal to the population mean and a standard deviation that's equal to the population standard deviation divided by the square root of the sample size. That's a normal distribution with a mean of 920 and a standard deviation of 870 over 100, which is to say a normal distribution with a mean of 920 and a standard deviation of 870. Now we're going to be interested in this 1,000 number right over here. So let's normalize that 1,000. A z-score is equal to the number minus the mean divided by the standard deviation. For us, that's 1,000 minus 920 over 87. That rounds to a z-score of 0.920. And I'm just taking a look over here and look how sneaky they are. They're putting a 0.92 there. Even though that is a z-score and not a probability, that is not the correct answer. That's something that I expect to see on every well-made test. They put the z-score as one of the answer choices because they know you're rushing it. Okay, let's get to our proportion then. The proportion of the mean claim is greater than 1,000. That's the same thing as the probability on the z-curve of z being greater than 0.920. On my calculator, let's do this both ways. The first way we're going to do this is using z-scores. So we're going from 0.920 to a large number, which is 1 E99. Oh, wrong number. Sorry, 1 E99. Ooh. Let's start over again. There we go, 0.920 to 1E99. Mean is 0 and standard deviation is 1 because 0.920 is a z-score. And that gets us to 0.1788, which is probably going to be the correct answer. Let's compute this in the other way, because this is a calculator multiple choice test, and of course you can. So we want to know greater than 1,000, so we'll put a 1,000 here. The mean is going to be 920, and the standard deviation, that's going to be 870 divided by the square root of the sample size, which was 100. So notice you don't even have to do all of the mathematics here, just chuck it into the normal CDF. Also, I noticed I forgot the division sign, so now that that's in there correctly, we can calculate, and we should get something really close. Yeah, 1789. So close enough. These two are very close. That gets me to our correct answer of letter C. And that's the end of our practice final. I wish you all good luck on your final this semester, and we'll see you next semester. Good luck, everyone.